Okay, we're back with this example of a cylinder rolling down an incline. And in order for us to proceed with this problem, we will need to understand conservation of energy in the sense of rotation. So I'm going to go ahead and now go to our textbook, and it talks about this kinetic energy with rolling down an incline. Okay, so or actually energy in general. Okay, so in this example, it's talking about 3 cans of soup with identical masses, and they're going down an incline. Okay, and assuming that there's no losses due to friction and only one force doing work, which is gravity. Okay, we'll go ahead and look at this conservation of energy. Okay, so let's see. It also states that the total work done is the change in energy and kinetic energy, and as the can start moving, the potential energy is changing into kinetic energy, right? Or we can also state this potential energy initially changes to our kinetic energy in the final position. Okay. Or we can also say that our potential energy due to gravity equals our kinetic energy plus our rotational kinetic energy. Okay. Our translational kinetic energy plus our rotational kinetic energy. Okay, and we can rewrite that in such a way that mgh equals 1/2 mv squared, so that's our normal kind of potential energy and kinetic energy, plus our rotational, which is what we looked at earlier. Okay, so we can go ahead and use this idea in order to solve for that speed. Okay, so let's go ahead and do that. We are going to take that equation, and I'm going to write it down here. So our potential energy due to gravity equals our kinetic energy translational plus kinetic energy rotational. Okay, and that's mgh equals 1/2 mv squared plus 1/2 I omega squared. So again, we're going to use this idea of conservation of energy to solve for the final speed of the cylinder. Okay, and that's going to be this term here. So that's what we're looking for. Okay, so we know our mass. I'm going to go ahead and check some things off that we know. Okay, so we know our mass. Oh, that's bright. Let me do black. We know our mass, we know gravity, we know our height at which it falls. Again, we know our mass. Has some radius, it has some mass. We will have to determine our I here and our omega. Okay. So, let me see if we can use another equation here. So, omega squared equals omega naught squared plus 2 alpha theta. But we don't have a theta. We also don't have an alpha. So let's see what else we could use. We know our I is going to be, we have a cylinder, got a central diameter, central axis. Okay, it will be mr squared over 2. So we have a solid cylinder about a cylinder axis. Let's see what else there is. okay, we can put it in terms of velocity only by translating it. Since v equals r omega, we can go ahead and use that. I believe that should work. So this should be v over r, since omega equals, or I'm sorry, since v equals r omega. So we can plug that in there. Our I, again, was, I believe it was, I gotta go back. Can't remember. 1/2 mr squared. Okay. So that should do it. Okay. So what I'm going to do is I'm going to plug those in and then try my best to solve for some kind of v, and then we can go ahead and solve the problem. Okay, so again we have mgh equals 1/2 mv squared plus, this is going to be 1/2 times 1/2 mr squared times v over r, this whole thing squared. Okay. You may notice that every single term has a mass in it, so we can actually cross those out. Okay. These two terms, our radii, can be crossed out. Okay. And so what we're left with on this right side is 1/2 v squared plus, it's going to be 1/4 v squared. Okay. And that is the same as 3/4 v squared equals g times h. Okay, so my v squared equals 4 divided by 3 times gh, or 9.8 meters per second squared, times my height, which is 2 meters. Okay, and we will need to square root that since there's a square here. So my velocity will be equal to the square root of 4/3 times 9.8 times 2. And that gives me a velocity of 5.11 meters per second. Okay. So that's my velocity of the can, or the cylinder rolling down the incline. All right. So let me go back to my PowerPoint. Skip through all that and continue with angular momentum and its conservation. Okay, so again, we were just talking about energy conservation. Now we want to look at angular momentum conservation. Okay, and angular momentum is going to be labeled as L. Okay, so L, let me put my pen on. Okay, so L, and that is equal to my inertia, I, times my velocity, my angular velocity. Okay, so this is my angular momentum. You can compare that to momentum like we talked about, linear momentum, P, if you want. P equals mass times velocity. So it's the same kind of deal, right? So this is linear, but this is angular momentum, okay? The units are going to be kilograms meters squared per second. And we can relate this to torque in such a way that the change in angular momentum over the change in time is equal to our net torque, okay? And we can go ahead, and do a couple of examples with this knowledge. So let's go ahead and do that. So the first one is calculating the angular momentum of Earth. Okay, so again, my angular momentum L is equal to moment of inertia times our angular velocity. Okay, and I don't know those right offhand, but I do know that I is going to be some mr squared, and I don't know omega. So let me go ahead and pull up this example because it is given to us in that example, I believe. Okay. Oh, so we, first of all, are looking at a sphere, not just a circle. Solid sphere about any diameter, solid sphere, thin spherical shell. No, so we're looking at a solid sphere here because we're looking at the Earth. So it's going to be 2 over 5 mr squared. So that's going to be my term out front, 2 over 5 mr squared. And let's see. Okay, so here it has our mass and our radius. And okay, so let me go ahead and write that out for us. So our mass, 5.979 times 10 to the 24th kilograms. My radius is 6.376 times 10 to the 6th meters. Our omega, okay, is, remember, omega is going to be our angular velocity. So in one day, how many revolutions do? We do 1 revolution per 1 day, right? So we'll need to go ahead and translate that into seconds. So let me go ahead and do that really quickly. So in 1 day, there are 24 hours. In 1 hour, there are 3,600 seconds, okay? In 1 revolution, there is 2 pi radians. So doing that quickly, I will get 7.27 times 10 to the negative 5th, and that is radians per second, okay? So I can just go ahead and plug all of that into my equation here. So L equals 2 over 5 times my mass times my radius squared times omega okay. I can get, or I will get, I get 7.07 times 10 to the 33rd is my linear momentum. And remember that this will be kilograms meters squared per second, I believe. Yes, okay. So that is my angular momentum of the Earth. All right. Okay, so in the next one, I will go ahead and get started on another example.